In the end of the previous video, I advertised to some degree the main result that we're going to derive, namely that the electrons near the Fermi surface at low temperatures are going to form these bound states of two electrons, which are going to condense and form the superconductor. And now we're entering the technical part of the lecture, where we actually would want to get this calculation done and to see how it actually happens. And it connects somewhat to the calculations we were doing in the previous lecture, where we were studying particles in various potentials. So there we were dealing with single particle quantum mechanics, so it was an externally imposed potential in which a single particle was moving, or which was localized there. Now what we want to do, we want to study actually two-particle problem, with two particles here describing effectively the two electrons near the Fermi surface for the context of in the context of superconductivity. And it turns out that actually two-particle problems oftentimes in quantum mechanics reduce to single particle problems. And in this segment, I'm going to illustrate how exactly it happens. So here we're interested in analyzing this two-particle Schrdinger equation, and to make things general for the sake of lectures later in the course, I'm considering here actually two different particles with masses m1 and m2, but in the next segment we'll work with the two electron problem where m1 is actually equal to m2. So what we have here is essentially kinetic energy of two particles. So this corresponds to the p1 squared over 2m1 kinetic energy of the first particle plus p2 squared over 2m2 kinetic energy of the second particle, and the interaction between them, which we expect to depend only on the distance between the particles. And now we have a wave function that depends on both coordinates of the particle r1 and r2, and well, the right hand side is the usual energy times psi. So we want to solve this equation. Now the goal of this video is to show that actually instead of solving this complicated looking differential equation which depends on two vectors r1 and r2, actually can reduce it to the good old single particle Schrödinger equation that we already know how to solve. And to see how it happens, let's do the following change of variables. We will go from the coordinates r1 and r2, the actual coordinates of each individual particles, to this capital R and lowercase r. So the former represents the center of mass of our particles, so it's defined as so, and the second one is the distance between the particles, so the relative distance between particles r1 and r2. Now what we're going to do, we're going to rewrite this equation in terms of this capital R and lettercase r. So in order to do this, well, first we notice that the of course the potential energy depends only on the distance, basically by construction. We've chosen it this way. And the only non-trivial part which we have to analyze is this kinetic energy, the derivatives, these Laplacians which appear in these brackets. And so we're going to work with these guys now. So to calculate this part of the kinetic energy, we can focus for the sake of simplicity on just one component of this Laplacian. So the Laplacian is sum of second derivatives with respect to each of the directions in our problem, x, y, and z. So let's just focus on x. And in this case, the capital case x is going to be the center of mass, x component, and this is going to be a relative coordinate in the x direction. Now, in order to change the variables in the Laplacian, the derivatives, we can go from the derivative with respect to x1 to a derivative with respect to the capital X and lowercase x. And this transformation can be done by rewriting it as so. So we basically add, in some sense, derivative in the numerator and denominator. And so this derivative d capital X over x1 is calculated from here. And this derivative d lowercase x over x1 is calculated from here. And the first one is, as you can see, gives us m1 over the total mass, and the second one is give us basically minus sign. So this is the result of this derivative when expressed through capital X and small x. We can do the same thing, of course, for x2, and this is the result, with the only difference here being m2 and here being the plus sign. And that's pretty much it. So we can actually calculate the quantity that we're after, written here, by essentially squaring this result. So this would give us the x part of the Laplacian for the first particle, and this guy squared will give us the x component of the Laplacian for the second particle. So therefore this guy goes here, and this result goes here. And as you can see, if we square this operation, these derivatives, we're going to get the second derivative with respect to the center of mass, the second derivative with respect to the center of coordinate, to the relative coordinate, but also we're going to get the cross terms. And actually the coordinates were chosen in such a way that the cross terms in these two brackets cancel each other out because of the minus sign here and the plus sign here. So, well, you can verify this, of course, just by writing it down or just by staring at it for a minute or so, but it's going to be pretty clear. So if you put everything together from these two brackets after a straightforward calculation, this is what we're going to get. So this is essentially a result for this for the x component of this quantity we're calculating. And so a Laplacian in terms of x1 and x2 can now be written essentially as a combination of two Laplacians with the, there should be, of course, a plus sign here. There are no minus signs, so it was a typo. So the first Laplacian with respect to the center of mass involves the total mass in the denominator, and the second Laplacian with respect to the relative coordinate involves this guy, which actually is called the reduced mass. So another way to write it is as so, m1, m2 divided by m1 plus m2. And this is called reduced mass. So now we're in the position to actually put everything together. So what we have proven, as a matter of fact, is that minus h squared over 2m1 Laplacian with respect to 1, the kinetic energy, the first particle, minus h squared over 2m2 Laplacian of 2, the kinetic energy of the second particle, can be written as minus h squared over 2m1 plus m2 Laplacian with respect to the center of mass, minus h squared over 2 mu, the reduced mass that I introduced in the previous slide, Laplacian with respect to the relative coordinate. So if I stick it into the Schrdinger equation, I will get, therefore, the following. I will get minus h squared over 2, this Laplacian of r m1 plus m2, plus Laplacian lowercase r over mu, plus the potential energy and the interaction energy between the two particles, which depends only on this relative coordinate, acting on my wave function, and the right hand side is just the energy as usual. So what I see from this equation is that there is just one part which depends on the relative coordinate and which involves interaction, and this part represents essentially a free Schrdinger equation for a combined particle with the mass m1 plus m2. Essentially describes a free motion of two particles as a whole. So for instance, if they were to form a bound state, this is exactly what we're going to be discussing in the last video in this lecture. So this term essentially describes the motion of this bound state, this sort of molecule-like state as a whole. And so to sort of extract this overall motion, we can just look for a solution. This psi tilde of capital R and lowercase r can be written as a solution to this sort of free Schrdinger equation, which is simply a plane wave, as we know. It's e to the power I, some momentum of this bound state, or whatever it is, times capital R divided by h bar, times, well, the wave function, which depends on the relative coordinate that we actually want to find. And the energy of this motion from here is going to be just this capital P squared divided by m1 plus m2, well, twice m1 plus m2. So, which is just a parameter. It doesn't appear anywhere else in the problem, and we can just move it to the right-hand side, subtract the total energy from the total energy, this energy, and that's it. So the resulting, the final result that we're going to get, which does not include this term, is going to look. Let me just write it here. It's going to look as so. So it's going to be minus h squared over 2 mu. So this reduced mass. So this Laplacian, which I can write as d2 over dr squared, plus v of r, psi of r, and the right hand side is going to be this e minus p squared over 2 m1 plus m2. So let me just write it as e prime psi of r. Okay, and this, as you can see, looks like a single particle Schrödinger equation. So it depends only on the wave function, depends only on one coordinate. Everything else is exactly the same. The only difference is that here I'm dealing with some reduced mass. So let's say in the context of the problem of 2 electrons that we're actually going to study, so m1, so if m1 is equal to m2, so if m1 is equal to m2, so then of course the total mass is equal to equal to m 2m, and the reduced mass, this mu, is equal to m squared over 2m, or just m over 2. So therefore, in our electron problem, this guy is going to be just the electron mass. So just to summarize what we have proven by this sort of brute force, straightforward calculation, is that in the simple, two-particle problem in two-particle quantum mechanics, we can always, get rid of one sort of unnecessary coordinate which describes the motion of our two particles as a whole, and we can reduce our problem to the standard single-particle quantum mechanics, which makes things much easier because we can now use the results and some of the conclusions of single particle quantum mechanics that we discussed in the previous lecture.